Okay, today we'll look at two examples. Okay, the first example is on MPC with constraint. So you look at example 9. Now, example 9, you can go and read. Basically, the story is that there's a driverless car. All right, there's a driverless car. Okay, so there's a car. And this car is 1000 kg. All right, it's moving at a speed of 10 meters per second. So y dot is equals to 10. And detect a boy running across the road at a traffic light 15 meters ahead. So from here to here is 15 meters. So there's a boy at a traffic light. He's running. Okay. And so the car is under MPC control. So since it's 15 meters away, all right, so the MPC provide a braking force. And obviously, you need to brake and stop 15 meters. You cannot cross 15 meters. If not, you will knock down the naughty boy. Okay, so that is the question. So now we formulate it like that. So you start with Newton's law, F equals to ma. Okay, then you bring the mass down. So y double dot is acceleration. So this is acceleration. So this is m. This is the way we write things. So y double dot is acceleration. You bring it down, you will get this. Then we define the MPC control signal as force multiplied by as force over mass, and it is like that. So in the question, we will basically, the MPC will calculate delta U. And if you want to have the real delta U, then, which means the real force, then it's very simple. You just, whatever you get for delta U, you just multiply by 1000, and you get the real force to apply to the brake. Okay, so, but to make the number simple, I just calculate delta U. I mean, if in practice, the real force will be just whatever delta U multiplied by 1000, you will get the real force. Okay, so now y is the distance, and we will compute delta U. All right, and there is a maximum braking force. I mean, the car, the maximum braking force is 5000. So that, which means delta U, there will be a maximum of 5000. Mass is 1000. So this will be equals to 5. All right, there's a maximum. So that will be a constraint on the braking force that you can apply. Now, so last time when we do most of the time when we do model predictive control, we have a plant, a process. Then because the process don't have an integrator, we augment the process and include an integrator into the process. All right. So, but now we have the process contains two integrator because to get Y, you have to integrate 2 times. All right. This you differentiate 2 times Y, then you get the force. From the force, you integrate 2 times, then you get the output or the distance. So now you have 2 integrators, so we will not add any more integrator into the augment it into the process. So now we write down the state space equation, okay, which is quite standard. So we define Y as the state x1 and Y dot as a state x2. So to write the state space equation for the process, you basically, the way I write would be x1, x2 dot dot on the left side, x1, x2, x1, x2, no dots on the right side. Okay, then I have to fill up all these matrices and vectors. So how will I do? Then I look, oh, I will see a x1 dot, then I look, oh, Y. So I put a dot here, which means I must put a dot here. And then I say, oh, Y dot is actually x2. So x1, I will then write 0, 1, so that x1 is equals to x2. Okay, this is how I will fill in the blanks for this matrix here. Then I will look at x2 dot, then I see x2 is here. So if I put a dot here, I also have to put a dot here. So I got Y double dot. So I have to look at what is Y double dot. Then I go and look. Y double dot, which is x2 dot, is just nothing but equals to delta U. So I then will put a 0, 0 here. I put a 0, 0 here. Then I put a 1 here. So x2 dot is equals to delta U. All right, then my Y is x1, so x1 is here, so I put 1, 0 here. So that's how I will fill up the blanks. Okay, so that is standard. So after we got that from physics, then we put it into discrete implementation. I use the simplest one, forward difference. All right. So every time you see a dot, it's basically finding differentiation, is finding slope, tangent, gradient, they are the same. So if it is in discrete time, so if you have k here, then the next instant is k plus 1. Then if here is xk, then at this point is xk plus 1. All right, so the gradient or the slope or the tangent, to me, they're all the same, is this divided by this. So and normally over here is a sampling interval we call h. So which means this is x1. All right, this now is replaced by this. x1 at k plus 1 minus x1 at k, which means this value minus this value will be this vertical, divide by h, which is the horizontal. So this would be the gradient. All right, so that's why this is replaced by this. And then this would be replaced by this. So this is the straightforward forward difference to approximate your differentiation. All right, so now you only need to approximate this, then all this x1, x2 just becomes the value at that instant. So it's just x1, x2 is just x1, x2k, x1, x2k. All right, delta U is just delta UK, the value at that instant. So to make life easy, I just say H is 1 second or 1 millisecond or whatever, it is just 1. So you just then rearrange everything, you will then get your ABC, which is like that. Okay, so that is standard. Then now, to formulate the problem, you cannot kill the boy. So your y max, when you first start, y is the distance. So y max, you can go is 15. So the question say, consider 3 outputs and 2 inputs. So the 3 outputs, y, k1, k plus 1, k plus 2, plus 3 must all be less than y max, which is 15. Okay, and then the delta U must be greater than, because the maximum negative force, breaking force, is -5. So you cannot be -6. All right, it's minus because it's breaking force. So it's positive if it is accelerating force. So it just makes sense. All right, so y mean is -5, and this is where we got it from here. All right, the force is 5,000. That's the maximum that you can have, and it's used for braking, so it's a -5. So, okay, so that's it. You have formulated the problem into a model predictive control with constraint in y and delta U. Okay, so now, then this part, I think you go and look at all these 21, 26, 17, and 18 to get for you all this. Okay. Once you have all these numbers, then go and look at 15, 16, 17, and 18 to get you H, F, M, and gamma. Now, so M is related to the constraint. We have constraint on Y and constraint on delta U. So this obviously is this fellow here, and this is this fellow here. So you look at them one by one. You have a constraint on U max, on U mean. So you go back and look at your U mean constraint. So there's a U mean constraint here. There's a U mean constraint here. So you use this, you find out what is C2, it is given here. C1, C2 is here. You find out what is C2. Your U mean was 5. Then your C1 is this one. Then your U k minus 1. So you got this. Then you have a constraint on Y max. So you look, Y max is this one. So you have a 5 for your M, and then for your gamma is Y max minus F X. Okay, so you go and use this line and go and use the U mean line, this line, to form your M and your gamma. So you go back and look. All right, this, obviously, this comes from here. All right, your U mean, and then that goes inside your gamma, and this one comes from here. Okay, you go back to find the corresponding M it says that it is phi and minus 1. Gamma, it says that it's this and it's U mean. All right. This is the constraint for the Y max. This is the constraint for U mean. So you go and look. You will get this and this. You go and look. This is the M for Y max and the M for the U mean. So you will get this. You have to go through the maths. I mean, it's just look at the formula, then make sure you got the right number. You have to go through them. So after you got that, then the quadratic programming problem with constraint is formulated. All right, this is given here. So you basically write down this, which means you want to minimize J. But you must meet this inequality. So we already have H and F and gamma and M. All right, all those H and F and gamma and M. So you stick it inside here, you will get this. You have to do it. It's just tedious maths. And so this one must give you this, and this must give you this sets of inequality. All right, this inequality must give you this set of inequality. You stick your M inside here and your gamma here, you will end up with this. Okay, then, so that's done, is formulated. In practice, you just then, basically in practice, you stop here. You provide H, you provide F, you provide gamma, and provide M to MATLAB. Then MATLAB will just provide you with delta U and also provide you with a J. So that's, in practice, that's all that you need to do. Okay, all you need to do, formulate the thing up to here, then MATLAB do the dirty work, the calculation. But you must understand the number that MATLAB give you. So how to understand? We see what is meant. So we calculate for 2, K0, K1. Okay, so let's look at K0, K1. So from 23, so 23 is this. Okay, you put J into this side, then it is equal to 0. So this is a quadratic in delta UK. There's a square here. There's a constant. No, there's a square here to the power of 1 to the power of 2. Then this is a constant term. All right. So put this equals to 0. Put J over this side. Okay, so then you can solve for UK. So if you solve for UK, using the quadratic solution minus B plus and minus B squared minus 4AC over 2A, you will get this. Okay, now later on you will see why I get that. So let's start. For K equals to 0, initially the question says that x1 is y, so you are at 0. So this one, it is x1 is actually y is equals to 0. Because you are now 0 at this point in time. When you see the ball, you are 0. You apply the brake, y max is 15 meters. So at the instant you see the boy run out onto the road, you are at y equals to 0. You have y equals to 15 as the maximum that you can go. If not, you'll knock down the boy. So this one is x2 is the speed, and your car is initially traveling at 10 meters per second. Okay, then your F1, F2 is actually here. All right. So now this is 0, 0, 0. So it's k equal to 0. So you have to compute what is your F1, F2. So you go and stick in all this number inside here. All right. Since this is 0, because x1 is 0. So x1 is 0. X2 is 10. Minus 45, you get 35. So it's your F1. Then likewise, this is 0, this is 10, you get 15. So you put 35 here. You put 15 here. Okay. Then I put J equals to minus 100. So I put J equals to minus 100 here. So now I can plot x-axis is this, y-axis is this. If I do that, x-axis is delta k plus 1, y-axis is delta k. Using this number, for j equals to minus 100, I will get this circle here. Okay, y-axis is delta uk, x-axis is delta uk plus 1. Likewise, I want to minimize j1. So maybe I can get an even smaller value of j. So I try j equals to minus 102. So I put j equals to minus 102. Then I plot delta k plus 1 on the x-axis, delta uk on the y-axis. I will get a second ellipse. Okay. So the model predictive control, the whole idea is to minimize j. So the smaller the j, the happier. All right. So if I can, I would like to have j minus 102, which is better than minus 100. Of course, if j is minus 200, it's even better. But there are constraints. Some j you cannot touch because there's constraint. So now let's use the constraint and see where is the smallest j that they allow you to touch. So there are constraints, you see, there are constraints 24, 25, 27, and 28. Basically, IE1, IE2, IE4, IE5. All right. Basically, you have to satisfy all these 5 constraints. So IE1 says that delta UK must be greater than minus 5. So I look at this picture here. Delta UK minus 5. So that's why this is inequality 1. Must be greater than minus 5. So I will have to draw a line here, call it inequality 1, IE1, and I know that inequality 1 says that my answer must be above. Below is not allowed because of the inequality 1. Then IE2 says that delta UK plus 1 must be greater than minus 5. So I see delta UK plus 1, which is here, must be greater than minus 5. So minus 5 is here. I draw a line. So this is inequality 2, and it says that I must be on the right side. Left side is not allowed. Then inequality 4 Now, x1, what is x1? x1, let me see. x1 is 0, x2 is 10. Okay, so I must put a 0 here and a 10 here. So it's 15 minus 20. So it's this one must be less than minus 5. Okay, so I put here 27 actually give me delta U must be less than minus 5. So K delta 0, because this is K, now we are considering K. So this is UK must be less than minus 5. So I look at delta UK, which is here, less than minus 5. Delta UK less than minus 5. Minus 5 is this line. So inequality 4 says that it must be below. Okay. Then inequality 5. I go and log inequality 5. Inequality 5, you put a 0 here, you put a 10 here. You rewrite this equation, you will then get this. Okay, this one will give you this line here. This dotted line here. And it says that delta UK, all right, must, where is it? This delta UK must be less than this line. So it says that it must be here, below this line. So, okay. So after check, then I see, oh, it is obvious. I cannot, the only answer is this point here. This point is at J minus 100 and satisfy all the inequality, all right? It just, because my inequality is equal or minus, equal or less than. Okay. I cannot use J minus 102 because you see, this is above, this is above. It's not allowed by inequality 5. Okay, so which means delta UK is minus 5. So you're going to look delta UK MATLAB. So we will say delta UK is equals to minus 5. MATLAB will show you this answer minus 5. This is what it means. All right. They have a sophisticated called quadratic programming algorithm. They don't do it graphically. MATLAB will go through. I can't teach you quadratic programming, but this is what it means. So you will get delta U0 minus 5. So you stick it. So you put it here. That's U, delta U. All right, this one. So you go and calculate, you get x1, 10, 5. With 10, 5, you go and get the new, you repeat the same process. So I just repeat one more time for you, and then that's it, which is exactly the same. So then with 10, 5, you go and look at inequality 1, 2, 3, 1, 24, 25, 27, and then we see. So this one and this one is the same. So it's minus 5, minus 5. Okay, And this time round, I draw for you the contour minus 50. All right, you go and look. I draw for you the contour of minus 50 and minus 52. Just like before, inequality 1 at minus 5 says that UK must be greater than minus 5. So inequality 1 says this one. Okay, inequality 2 says that UK plus 1 must be greater than minus 5. So says that it is this one. It is only here. Inequality okay. Then this inequality says that U2 must be less than 0. How we get that? 10, 5. Let's go back and look at the inequality. So if you put a 10 here, minus 5, must be less than minus 5. So it is a 10 and a 5. So which one is 10 and which one is 5? 10, 5. So this must be a 10. This must be a 5. All right. So 15 minus 10 minus 2 times 5. This one must be equals to minus 5. So this IE4 says that UK must be less than minus 5. So we go and draw that in. UK is this one. IE4 minus 5 is here. So IE4 says that it must be less than minus 5. Okay. And then the last inequality says that, so this is 10. This is 5. All right, you bring this over, it will give you this equation. It will give you this equation. And with this equation, you go and draw IE5. And IE5 says that it must be less. So in the end, you have only one solution that satisfies all the inequalities, is this point here. All right, this cannot satisfy because this one you cannot satisfy IE5, you cannot satisfy IE4. Okay, this particular point satisfy IE5, IE4, IE1, IE2, everything satisfy. So the minimum you can ever get is minus J, minus 50. And the U should be equals to minus 5. So that's how you get UK. Now will be equals to, MATLAB will show you this answer, minus 5. Okay, so you can continue yourself. I show one more detail working for K equals to 2. All right, you can see for it yourself. Okay, go for a short break. Come back at 6:55. Then we'll do the last question. Yeah, I'll stop for a while. Come back at 6:55. Okay, this question basically deals with the following now. We say that I showed you this type of thing before. This is the real plant. All right. And we say, okay, this is the real plant. So I write down real plant. Okay. And this is the model predictive controller. And we say one of the most useful thing about the model predictive controller is that it can include a constraint in, let's say, U, like we saw the example. You can include a constraint on the power that is sent to the plant. Now, this question study, what if we don't constrain U? There's no constraint on U. All right, but actually in the real plant, there's a valve that chemical flow in, and there's a real constraint. When the chemical flow in, you open the valve, it's fully open, that's the constraint. You increase U further, the amount of chemical flow in cannot be, the valve cannot open more than it is fully open. All right. So what if you do not consider that in the MPC calculation? What will happen? So what will happen? Your MPC will calculate U as though there's no constraint. So in this question, just to make the number easy, I put a constraint, upper constraint here as 0.2. So MPC can calculate anything. It can calculate 0.5, but 0.2 is a real constraint. So the amount of chemical flowing into the plant is restricted to 0.2. Even though you output and say, hey, send in 0.5. All right, or the power or the voltage. All right, if your power supply, the upper limit is 0.2 or whatever, you can say I send in 0.5. Your power supply can maximum 0.2. Then you can the plant can only receive maximum 0.2 volts or 0.2 watt or 0.2 whatever. Okay, then if the MPC do not consider this 0.2 constraint in the calculation, what will happen? Okay, why? So to answering that question will tell you why we should include this inside our calculation. Because if you don't include, your performance is lousy, which means your MPC is no longer optimal. All right, and you don't get as good a performance as when you consider this constraint into the calculation. That would be obvious. That should be obvious, but let's go through the detailed calculation. So the question is basically that so that we go straight to the heart of the message, I will not do the preliminary, plant MPC calculation. So I take the same example in example 8. All right. So it's the same plant and the same MPC. So in example 8, you have this, And example 8 say B is 1, this one is 1, A is 1, C is 1. And example 8 is, let's go and look at example 8. All right, so this is example 8. When you calculate all this the same, everything is the same, you can follow all the calculation here. Okay. Okay, so you go and take all the RS, F, phi, R bar in example 8. Then you stick inside here, you will get KR is 0.5 and KMPC is 0.500, 0.5 and 0.3. In other words, inside here, this one is 0.5. This is 0.3, and this is 0.5, 0.3. All right, all this take from example 3. So in order to calculate delta U, R times R in example 3, this is 1, so it's easy. So 1 times this is plus minus this 0.5, 0.3 times your X. So you will get your delta U. Okay, then you integrate them, you'll get your U. All right, that's example 8. So if we do that, this is what you will get. So like example 8, when you first start, everything is 0. So everything is 0, so you get your x1, x2, which is defined in example 8 is this, so you get zeros. So then after that, what is the delta U calculated? So you take this, put inside here, this is 0, then this is 1, this is 0.3. So you calculate delta U is 0.3. Okay. Now, delta U is 0.3. The question say U max is 0.2, but your U now is 0.3. Okay, so what it means? It means that here you calculate is equals to 0.3. But you are stuck at 0.2. So the real input to the plant is equals to 0.2. So to use this, goes through your BP, AP, CP calculation to get what is your Y and your next XP. Okay, we will do that. All right, so we'll do that. So your XP, this one is 0.2, UP is 0.2, though U calculated was 0.3, but the real thing that go through this plant one is 0.2. So you calculate, you'll get X1 is 0.2, and X2, which is defined as this, is also 0.2. All right. So now what is the new delta U? You take this minus this. What is X1? x1 is 0.2, 0.2. You see, over here, the plant give your x1 that comes from the plant is 0.2, 0.2. All right? Because 0.2 go through this calculation, what comes out here is 0.2, 0.2. All right, y is 0.2, delta xp is 0.2, so it's 0.2, 0.2. If 0.3 goes inside here, then come here will be different. But since you calculate 0.2, 0.3, but what really goes inside here is 0.2, so what comes out is a result of this 0.2. So I think the idea is clear. So you get this as 0.14, and u will be this plus the previous delta u is 0.14 plus 0.3 is 0.44. All right, so now you get 0.44 here. Okay, you send 0.4, but you know you're stuck at 0.2, so it will still receive you will still have to use 0.2 for up, goes through this calculation to get your x. Okay, we'll just do one more round. So 0.44. So now up1 is 0.2. So you have to take this and stick inside here. Okay. Sorry, not that one. Yes. Stick inside here. Okay. So you get 0.4. Then x1 is defined like that. You get 0.2. So you got the new 0.2, 0.4. Then you go through your MPC calculation, you get 0.08. Then U2 is this, you get 0.52. So likewise, 0.52 is actually what you calculated inside here. Then actually, but what goes in is 0.2. So, and then you continue and continue and continue. So this is what will happen. Now you see, so since it's repeated, I will not go through the detailed calculation. You see from here to here, XP is always stuck at 0.2. Your U that was calculated is more than 0.2. You see for this range, my U is greater than my UP, which is equals to 0.2. All right. Only when your U is less than 0.2, which is from here, your U is less than 0.2, then you will get your U is less than 0.2, then what you get is U and UP is the same. You can see, because if your MPC calculate the number here is less than 0.2, it will not get stuck at 0.2, so it will be equal to UP. So that's fine. So it goes through this calculation, come here, then calculate if it is less than 0.2, then U will be equals to UP. All right, so you can see here, this set over here. Now you look, I think I plot the 4.12 for you to see, 4.12. So I plot UP, which is always stuck at 0.2 or less. This is U. This is the Y. All right, you basically see once it is less than 0.2, because this is sample by sample, then the U, this part U is equals to UP. Okay, so now we do the next question, and that is formulate a quadratic program with constraint u less than u max. All right, which means now, oh, I know that I will get stuck at point 2 anyway. So inside this MPC, I'm going to do a MPC calculation with constraint of u max 0.2, so that what goes out in u will always be less than or equals to 0.2. So if that is the case, then forever UP will be equals to U, because U is forever less than 0.2. My calculation inside MPC ensures that. Okay, so we look at that. That is a standard MPC with constraint that we have done before. So I'll go through it quickly. So you go back and look at your 15, 16, 17, 18, you will get your H, your F, your M, and your gamma. All right, this, you look, there's a U max inequality, M and gamma. So you go and look at what is the M and what is the gamma. It's a U max inequality. No, is this one. So you go and take out this. This would be your gamma, your M is C2. So you go and see what is your C2. All right, and what is this? What is your C1 and UK minus 1? So that would be your M and your gamma. If you look, then it is given here. All right, M is 1, gamma is this one. Okay. Then after that, you do the quadratic programming, is 13 and 14. So 13 must give you your J, 14 must give you this. Okay, then stick in your H, stick in your F, stick in your M, and stick in your gamma. You write it out, you will get this and this. Okay, then it becomes a very standard MPC with constraint calculation. So I just do a few rounds for you. When we first started, everything is 0, so this is 0. Then U is this, without constraint one, is calculated to be 0.3. You put this in here, put this in here. All right. This is this one. This is this one. Now, delta U, this constraint says that this is 0.2 minus this is 0. So a constraint of 0.2. So in practice, you throw this quadratic programming problem into MATLAB. They will compare 0.3 and 0.2, and they tell you, okay, the minimum should be 0.2. So they'll take this. Then they throw back to you, your delta U is 0.2. Okay, because you must be less than 0.2. Your 0.3 is more than 0.2, so cannot. So they will say 0.2. Okay, so then delta U is 0.2, then U is just delta U plus the previous one, which is 0, so it's 0.2. So output is 0.2. Then, which means this is delta U. Okay, so this is delta U, you throw it in, so you get 0.2 for the new one, then you go and calculate, you get 0.14. So again, the MATLAB will compare this with the constraint. The constraint 4026 says that your delta U must be less than 0 or equals to 0. So this one cannot. So MATLAB will show you this one. So therefore, your delta U, MATLAB will give you this one. So you have to calculate your U is this one plus the previous one is 0.2. So you give you 0.2. Okay, so we went through 2 rounds. So you look, the answer is here. Throughout, because MATLAB always ensure that your delta U, your U is less than 0.2. So that's it. You will never cross, U will never cross. U will always be less than or equals to 0.2. Okay, so no problem. So therefore, you will always be equals to UP. So what the plant received will always be what the MPC calculated. So you look at Y, I plot out for you. So this is what you will get. You see throughout this line here, throughout this line, U and UP is the same. Okay, this is Y. Now, if you compare, you see Y goes all the way here, set point is 1. Basically, it just crosses by a little bit of overshoot. Maybe it's overshoot of 1.1. Then it comes back. I think if we extend, it will just go to 1 very quickly. Okay, the performance should expect to be like that. You look at the previous one, this one, you see, it goes all the way up to overshoot is 1.4. Then come here, and I don't know when it will go to 1. Okay, so you compare the performance of this by 10 sample. This is still, so far away. By the 10th sample, you're basically at 1 already. If you are patient enough, I will do a few more, then you draw a few more, you'll see that it's settled to 1 very quickly. Whereas this one, I give you a longer table, maybe after K equals to 20, then it's settled down. Okay, so you can see the performance is very different. The last part, there is a simple thing. If you don't use MPC, you use PID or you use MPC, there is not a clever thing that you can do, but you can tune the MPC such that your U here is always less than 0.2 without the constraint. Which means without constraint calculation, I can make KMPC and KR small value so that when you calculated this one, U are small, the value is small. Means what? It will always be less than 0.2. So then forever you will not hit the real constraint of 0.2. You can do that, which means you don't do quadratic programming, you don't do inequality, you just basically choose a small weight. All right, we will see that's part 3. A small weight in the MPC calculation, then you get a small value of MPC gains. That's part C. Let's see that. The disadvantage of that, then if you have a very small gain, then your control output will be very very slow. Okay, let me see, where is it? Okay, question is part D. So to get that, what's part D? Okay, you choose a weight to be 40. 40 RW, if you go back and when I first teach you MPC, you see where does it comes in. You see, when I first teach you, I show you before, this R, if which is a big number, then they are saying that your delta U is very expensive because it is multiplied by a big number. It has a big contribution to J. Then it will give you the optimization program will give you very small delta U. All right, because big delta U will contribute a lot to J because the the R bar here, which contains the weighting RW, is large. So by choosing large, this one, it will relatively ignore your Y and only concentrate on this. So all the J is trying to do when you minimize J is to minimize U. All right, that is what. On the other hand, if RW is small or zero, then they don't care about you. You can be very big, or that they don't care about you. All they do is just to optimize Y. But if R is very big, very, very big, then all by optimizing J, all they are doing is optimizing U. Make U as small as possible, since you are making J as small as possible. Okay, so R, which contains RW, give the relative weights between this term and this term. So now in this question, we choose RW to be large. All right, 40. I think previously was smaller than that. Okay, so then we do the standard MPC with no constraint, the one that I first teach you in first lecture. Then you will find what you get is KR is small, KMPC is also small. All right, 30 and 31 will give you this. So delta U calculated is using this one, this stick inside here, this stick inside here. This question R is always 1. So when we first start, this is 0. So you calculate this is delta U is 0.067. So U is this one. K equals to 1. You take this inside here. Calculate, you got X. So you do this here. Delta U1 is this. Then after that, you basically just continue and continue. The steps, the answers are all given here. You see, because I make it a point, even without all the inequality constraint, since calculated U is always less than 0.2, so U and UP is the same, no problem. You will not hit the real physical constraint of the valve or the power supply. So these two are always equal. Then you look at the output Y, this is the one. All right, U, which is equals to UP, is very small. All right, you see less than 0.2, always less than 0.2. Then this is Y. Okay, it is obvious. Y is not good. Okay, at 10, it is still here. So 1 is here, so maybe it will, don't know how. I don't know. Okay, I don't know. You have to calculate how many sample before it goes to the set point of 1. All right, 1 is here. Okay, so obviously if you compare the three, the best performance is this one, whereby the MPC consider the constraint of 0.2 in its calculation. Okay, I've finished teaching you everything that I want to teach. Any question? All right, if not, remember to submit your report by next Tuesday to Canvas.